In this module, we'll extend hypothesis testing and confidence intervals to the comparison of two population means. We'll use the same three cases as we did for the one sample cases. Let's get started. It turns out that comparing two samples is actually much more common than the one sample case, but the one sample cases are naturally extended to the two sample cases. We'll start with some basic assumptions. There are two groups to be compared, and the response to be compared is measured on an interval or ratio scale, such as temperature, speed, length, or time. You get the idea. We'll call the first group X and the second group Y, but it doesn't really matter which is which as long as you keep track of it. The X's and Y's have to be a random sample from a population, and the samples have to be independent of one another. We'll start with case 1, where we'll assume that the population being sampled is normal, and the population standard deviations, sigma 1 and sigma 2, are known, and that we want to compare unknown population means mu 1 and mu 2. Suppose we have two types of steel that we have tested and the yield strengths on. We have tested M equals 20 samples of cold rolled steel and N equals 25 samples of galvanized steel. For now, let's assume that we know the population standard deviations, perhaps from lots of experience with these types of steel, to be 4.0 and 5.0 for the cold rolled and galvanized steel respectively. We want to test the hypothesis that the two population means are equal versus a two-sided alternative at an alpha equals 1%. Furthermore, we are willing to assume that the two populations are normally distributed. The sample mean of the 20 samples of cold rolled steel is 29.8 ksi, and the sample mean of the 25 samples of galvanized steel is 34.7 ksi. We want to see if these sample means, given these standard deviations, could have occurred by chance. In the one sample case, we formed a z-statistic and compared it to a standard normal distribution. In the two sample case, we'll also form a z-statistic and compare it to a standard normal distribution. Of course, the interesting part is the denominator of the z-statistic. Where did that come from? As long as we are willing to assume that the two samples are independent, then we can use some rules from earlier in the course to derive the variance of the difference between two means, as we see here. With the confidence that our z-statistic is properly formulated, we can go ahead and determine the rejection region for our statistic. Since we are conducting a two-sided test with an alpha of 0.01, we need to look up alpha over 2 of 0.005, and we'll see that that corresponds to a z of minus 2.576 and plus 2.576 for cutoff values. You can actually find this quickest in most books by looking at the bottom of the t-table, where an infinite number of degrees of freedom is listed. The t-distribution approaches the normal distribution as the degrees of freedom approach infinity. So if we substitute in our numbers from our example and do a little algebra, we find that z equals minus 3.66, which is less than minus 2.576, so we reject the null hypothesis that the two populations have the same mean. Calculating the beta values is done pretty much the same way as in the one sample case. Of course, the actual value of beta depends on the true difference between the population means, as well as the standard deviations of the populations and the size of the samples taken. Here are the formulas for beta for each of the one-sided and the two-sided alternate hypotheses. In case 2, the population standard deviations are not known, and the distribution of the two populations may not be normal. But we have taken sufficiently large samples from each population for the distribution of the means to approach a normal distribution, and for the sample standard deviations to be a good estimate of the population standard deviations. From there, as before, we just substitute the sample standard deviations into the formula for case 1 and proceed as before. Recall the one sample confidence intervals? Here are the one sample 95% confidence intervals for case 1 and case 2 that we saw before, along with the more general case 2 formula. Let's see if we can extend this idea to the two sample situation. It's relatively straightforward to show that the confidence intervals for case 1 and case 2 are shown here. Note that these confidence intervals on the difference between two means. If the two populations have the same population mean, this interval should contain 0. Case 3 is a little more tricky for the two sample situation. Let's start with a review of the one sample situation. In the one sample situation, we have a sample of n observations from a normal distribution that we use to calculate a t-statistic, which is compared to a t-distribution with degrees of freedom equal to the sample size minus 1. In case 3, for the two sample situation, we are assuming that both samples come from normal populations, and we again form a t-statistic that we're going to test the null hypothesis, just as before. The formula for the t-statistic was pretty predictable, but what degrees of freedom do we use when we look it up in the t-table? Each population has its own variance, and each variance has its own associated degrees of freedom, depending on the size of the sample taken from each population. We need to find the degrees of freedom for the combined variance, but as it turns out, that can't be done exactly, at least for the general assumptions. We can approximate the degrees of freedom with the formula shown here. It's a bit messy, and you'll need to round it off in order to use the t-table in the book. Should you round up or round down? Most people will round it to the nearest integer, but a more conservative approach would be to round down to the next lowest integer. See if you can figure out why this is a more conservative approach. The need for messy degrees of freedom stems from the fact that in case 3 we've made no assumption about the relative size of the two variances. If you are willing to assume that the two population variances are equal, then we can follow a different testing strategy. First, we combine the two variance estimates into one pooled variance as shown here. Then we use this pooled estimate in the test statistic. The pooled variance will have m-1 plus n-1, or m plus n minus 2 degrees of freedom. Here's how the pooled variance is used to form the t-statistic. With this approach, we'll end up with an integer for the degrees of freedom, so we don't have to worry about rounding it off. How willing should we be to assume that the two population variances are equal? Well, it's safer just to use case 3, where we don't assume they're equal, instead of case 3 prime. Even if the two variances are equal, the first case 3 will still work out. However, virtually all extensions of two-sample tests to more samples are based on case 3 prime. That is, these extensions all assume that the standard deviations are equal. We would generally at least use graphical checks to see if this assumption is reasonable, and there are hypothesis tests that can be used to test this assumption explicitly. Just as in the one sample situation, calculating beta for case 3 is quite complicated, so we will generally rely on statistical software to help with this. Here are some of the things you should be able to do as a result of viewing this module and completing the associated assignments.